Hey there, Mr. Sutton here with the AB Calculus 2-6 Extra Practice Number 3 solutions on continuity. For this problem, we're finding intervals of continuity for this function here. So the only discontinuity is we have an infinite discontinuity at x equals 7. So therefore, we have an interval of continuity from negative infinity to 7, and also from 7 to positive infinity. And we're going to have to use parentheses on all of these. In trying to find the intervals of continuity on this graph, the first thing we observe is that this function appears to be continuous everywhere. We do have a horizontal asymptote on the x-axis, but that doesn't cause any breaks in the graph. So the interval of continuity then is just negative to positive infinity. To find intervals of continuity on this problem, we first look for discontinuities, such as the jump at x equals negative 5. And then the interval of continuity is just everything but that. So negative infinity to negative 5, union negative 5 to positive infinity. To find the intervals of continuity for this function, let's take stock of some key features here, such as we have an endpoint at negative 1 and also at positive 3. And in between, we have a jump discontinuity at 0, x equals 0. And we also have removable discontinuities at 1, 2, and if you want to count it, 3. So moving ahead then and writing the intervals of continuity, we're just going to leave all of these out, including the undefined area that's beyond the endpoints. So our first interval of continuity starts at the first endpoint. We're going from negative 1 until that jump at 0. Union, we have to go from 0 to the whole at 1, and then from 1 to 2, and from 2 to 3. For this problem, we're being asked to identify all points of discontinuity and their type. So for this one, since we have a rational function, that means we have to look out for removable and infinite discontinuities, holes and asymptotes. To figure out what they are and which is which, let's factor out this denominator. So that's going to be x plus 2, x minus 2. And anything that cancels out a common factor is going to give us the possibility of having a hole. Since nothing cancels out here, the things that zero out my denominator, negative 2 and positive 2, are both going to be asymptotes, infinite discontinuities. On this problem, we're trying to find points of discontinuity and what type they are. Now, cotan, you might recognize, this is one of those 4 trig functions that has asymptotes because it's the quotient of one or more trig functions. Cotan, for example, is cosine over sine. So this is going to have vertical asymptotes wherever sine takes on a value of 0. Well, where does that happen? Sine is going to be 0. The y value on the unit circle is going to be 0 at 0 radians, also at pi radians, or 180 degrees, and also at 2 pi radians. So at those 3 spots, we're going to end up with infinite discontinuities on this interval. For this problem, we're trying to find points of discontinuities and what type they are. Since this is a square root function, we have to be on guard against undefined areas, and those are going to occur wherever the thing inside the radical, the radicand, takes on a negative value. It's okay to take the square root of a negative or a positive, a 0 or a positive, but taking the square root of a negative, that's a big no-no. So we'll say undefined areas where 6 minus x specifically is less than 0 is negative. And then if we subtract 6 from both sides and divide by negative 1, that's going to reverse the direction of the inequality. So we have an undefined area for all x values that are greater than 6. And if you try one of these like 7, well, 6 minus 7 is a negative number, and again, square rooting that doesn't work. For this problem, we're trying to find points of discontinuity and their type. X sine of x, well, that's the product of 2 functions, so we have to kind of look at them individually. X by itself is just a line. That has no discontinuities. Sine of x, we know, has no discontinuities. That's just a smooth sine wave that just keeps going. Since these are both continuous functions, that means that the product of these things will also be a continuous function. So no discontinuities at all, and we just move on. For this problem, we want to know if this piecewise function is continuous at x equals 0 specifically. And the reason we care about that is because that's the border value. So that means that we have to test out the limit, the function value, and then compare those to see if they're the same at that border value. So let's first look at the left side limit as x approaches 0. That's going to use this before 0 rule here, 15 minus x squared. That's going to be 15 minus 0 squared, which is 15. And now we also have to look at the right side limit at 0. That'll use the second rule, the after 0 rule. So we're going to be doing 2 times 0, which is 0. Well, 15 and 0 don't match up, so that means that my limit, my overall two-sided limit, does not exist, and that means that my function is not continuous at x equals 0. On this problem, I want to know if this function is continuous at x equals 0. So let's start by finding the left side limit at 0. That's going to be using this first rule, the before 0 rule. So 3 minus 0 gives us a limit of 3. And now the right side limit at 0 is going to use this second rule, the after 0 rule. So that's going to be 3 plus 1/2 times 0, which is also 3. So our limit exists. Let's also look at our function value. Function value is going to use the first rule again. So f of 0 is just going to give us 3. So the limit is 3. F of 0 is 3. Since those two things exist and also equal each other, we can conclude that our function is continuous at x equals 0. On this problem, we're given this piecewise function f, and we want to know for what values of b, where b is this little mystery constant in here, this function is going to be continuous at x equals 2. So fastest way to do this is basically just to pretend that this thing already is continuous and just try to prove the continuity at x equals 2. So we have to start by making sure that the limit exists. The left side limit as x approaches 2, that would be e to the b times 2, because you have to use the less than 2 rule for the left side limit at 2. So we could write that as e to the 2b. And we also have to talk about the right side limit at 2, which uses the after 2 rule. So that would be 1.5 times 2, which is 3 plus b. And if we're doing continuity, we also have to consider the function value at 2. So f of 2, which happens to be exactly the same as the left side limit, e to the 2b. All right, so for this thing to be continuous, the limits have to equal each other. So we can say e to the 2b equals 3 plus b. And the limit has to also equal the function value, which happens to already be e to the 2b. So this is something we're going to have to solve on a grapher. Let's go ahead and do that now. So here's my calculator. I'm entering each side of this equation into a y equals, and I'm using x instead of b because that's what my calculator likes. Now for the window, just looking back here, we've got possible answers here, intersections, that are going from all the way back at -3 to, well, I think as far forward as we go is +1. So let me just go back to my grapher, and for window, well, let's make it -4. So going from -4 to, I don't know, let's say, yeah, let's do +1. And then zoom 0, let's see what we get. All right, so there's my exponential. There's my line. And now I have to do second trace, pull up my calc menu, and option 5, intersect. And let's go back here, press enter 3 times and see what the intersection is. So 1, 2, 3 gives us about -2.998 back there. And there's another one though. We've got this other intersection point up here. So doing second trace, option 5, intersect, and move my little spider forward to that intersection spot. It's about the journey, not to that destination, right? So there we go. Enter, enter, enter. And that's going to be 0.647. So those are the two b values that make this thing continuous, roughly, approximately. So that gives us answer choice D. On this problem, we're given the g function above here, and we have this mystery constant k as part of it. We want to know what k value makes g continuous at our border value of x equals -3. Now this is kind of an interesting piecewise function because we have one rule for the value where x is -3, and then we have one rule for essentially everything else. So in order to figure out this k value, since they're telling me basically that we're trying to make g continuous, let me just go ahead and do one of my continuity proofs, and I'll just keep k around until I can actually assign a number to it. So if I'm proving that g is continuous, I have to show first off that the limit exists, then that the function value exists, and finally that those two things equal each other. Let's start with the limit. So to take the limit of g as x approaches -3, which of these rules am I using? Well, I have to take basically numbers as we're getting close to, but not exactly equal to -3. So that means I have to use this first rule that has all of the numbers that are not equal to -3. So in order to take the limit here, I would normally just plug -3 into this function, but if you do that, you'll notice you get, let's see, 9 minus 9, which is 0, over -12 plus 12, which is also 0, so that's no good. We're going to have to factor and cancel before we can take the limit. So let me rewrite this. I can rewrite my numerator as x plus 3 and x minus 3. So now I'm taking my limit as x approaches -3. So there's my new numerator. And for the denominator, I can factor out a 4, leaving me with x plus 3 inside there. And now I can cancel out those x plus 3's, which was causing me to get 0 over 0 when I plugged in -3. So that comes out to x minus 3 over 4. And now if I plug in -3, well, that's going to be -6 over 4, which is going to be, let's see here, -3/2. Okay. Now the other piece of this is I have to talk about the function value. I found limit of g as x approaches -3. I also have to talk about g of -3, the function value. G of -3, I just use this rule where x equals -3, and this rule automatically gives me a constant value of k, no matter what I plug into it. But there's only one thing I'm allowed to plug into it anyway. So there's our function value. K is a constant, so that means it exists. So the only other piece here is that the limit and the function value have to equal each other, which means we can say that k and -3/2 are equal to each other, which means k is -3/2, choice B.